Welcome to Section 4.4, the equidistant theorems. Our objective is to recognize the relationship between equidistance and perpendicular bisection. For our homework, we have on page 188 to 190, 4 to 14 the evens, and 20. So here we go. First we have some definitions. The first definition, the distance between two objects. So here's what we're defining, what it means to be the distance between two objects, is the length of the shortest path joining them, which seems simple enough, but really isn't once we start getting into proof. Now a postulate that goes with this says a line segment is always the shortest path between 2 points. So if you were to ever connect 2 points, that's going to be your shortest path. So not taking different segments to get there. Our next definition. The perpendicular bisector of a segment is the line that bisects and is perpendicular to that segment, which we actually talked about in the last section a little bit. If you have any questions about these definitions, make sure you make note of it. So if you can't picture what I'm talking about, let's make sure we go through it tomorrow in class. So here we go. We have two theorems. Our first theorem states, if 2 points are equidistant from the endpoints of a segment, then the two segments determine the perpendicular bisector of that segment. Now, let's go ahead and draw out what that looks like. So here we go. Let's say that we have a segment right here. Say that's segment AB. And we have 2 points. We'll call this point C is an equidistant from the endpoints, so it forms an isosceles triangle. And let's say that the same thing happens here with point D. That's also an equidistance from the endpoints, so it forms another isosceles triangle. What this theorem says is when you have these 2 points in equidistance from the endpoints of the segment, then if you have a connection between these 2 points, what that means is that segment CD is actually going to be the perpendicular bisector of AB. So that's what that theorem says. Now our next theorem says, if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of that segment. So it's going to work in reverse. So here we go. Let's say that we have segment AB and segment CD. And let's say that we know off the bat that CD is going to be the perpendicular bisector of AB. What that means is any point on the perpendicular bisector is going to be an equidistance from our endpoints, which means C is going to be an equidistance from A and B. That means D is going to be an equidistance from A and B. And any other point that might fall on this line is also going to be an equidistance from A and B. And that's how that theorem is going to work. Okay, so let's try our first proof that's going to use this. Now, we're trying to prove that AE is a perpendicular bisector of AD. So here we go. I'm going to go ahead and get started with this proof. So I got my statements and my reasons. And my givens. Angle 1 is congruent to angle 2, and angle 3 is congruent to angle 4. Those are going to be my givens. 1 is congruent to 2, 3 is congruent to 4. Now, unfortunately I have a lot of options here. I want to show you how those theorems work though. So don't jump the gun and start adding and doing some reflexive stuff. Don't bother with that stuff. Instead, let's look at this top triangle here. If the two angles are congruent, then the two sides are congruent. So I'm going to say that AB is congruent to AD. If angles, then sides. Now, my next triangle, the lower ones. Again, 2 congruent angles. 2 congruent angles, then 2 congruent sides. I'm going to say that BC is congruent to DC. Same as number 3. put those tick marks in. And what I see here is that I have 2 points, points A and point C, that are both the same distance from B and D. Anytime I see that I have that, what it ends up looking like is 2 isosceles triangles with the same base. What I can say then is that AE, which AE is going to be going all the way through, it meeting at C here. AE is the perpendicular bisector of BD for a reason. If 2 points are an equidistance from the endpoints of the segment, they determine the perpendicular bisector. So again, 2 endpoints, equal distance from the endpoints. Those 2 points, when you connect them, they make the perpendicular bisector. E being a point on the perpendicular bisector. Okay, here's our last proof, and a proof for you to try on your own. We're trying to conclude that BE is congruent to ED. And here's what's known to us. Now, those equidistance theorems are actually shortcut theorems. There are much longer detour ways of actually proving this stuff. Whichever way is going to work for you, though, let's go ahead and use that. Press pause, see if you can get to this. When I do it, I'm going to be using my equidistance theorems. So go ahead, give it a try. Okay, so here we go. Got my givens written down. I've marked up my pictures. Now, I don't quite see 2 isosceles triangles here. Does that mean I can't apply my theorem? No. I have 2 points. I have point A and I have point C. They're both an equidistance from the same segments, BD. What that means is I can put down that AC is the perpendicular bisector of BD for my reason. If 2 points are an equidistance from the endpoints of a segment, they determine the perpendicular bisector. Okay, next, since we have AC, which goes all the way through and hits E in the process as well, E is a point on my perpendicular bisector. And if I have any point that's on my perpendicular bisector, it's also an equidistance from my endpoints. So for my final step here, BE is congruent to ED. For my reason, if a point is on the perpendicular bisector of a segment, its equidistance from the endpoints of the segment. Now, there were other options. What other options did we have? I'm going to erase my tick marks here just so that you understand this. Just with our options here, what we could have said here is we could have ended up proving that my top 2 triangles were congruent by showing reflexive right here. With my reflexive right here, I would have had side, 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 and side, side, side. Now, the next thing that I could have done here is I could have ended up through CPCTC proving these 2 angles were congruent. Showing another reflexive piece right here. AE was congruent to AE, and then I could have gotten these big triangles to be congruent by side angle sign, in which case BE would be congruent to ED by CPCTC. So we could have used a detour as well. Instead, I got my proof done using the equidistance theorems and in 4 steps. I will never make you use these equidistance theorems. However, you will kind of notice as time goes on, if you use the equidistance theorems, your proofs can get reasonably short instead of being somewhere in the 20-step range. Okay? If you have questions, bring them to class tomorrow. We need to make sure we're answering our questions. last but not least, the answers to our homework. You'll see here the proofs aren't very long, but the proofs are also using the equidistance theorems that we were talking about. If you're not practicing with those equidistance theorems, you're not going to get a hang of them. I'm going to encourage each of you to really try and get a hang of these equidistance theorems. They make your life so much easier and your proofs so much shorter. So try your best on these, and we'll see what happens. Have a good one.